is breadth first search. So it's traversing a graph one level at a time. There's a couple ways to implement it. Using a queue is the most time efficient and is kind of like the easiest, the most intuitive. The time complexity of this is O of m plus n, where m is the number of edges and n is the number of nodes. So for a binary tree, it would just be O of n because you just there's only two edges from each like nodes, so it'd be 2n plus n, and then you can drop the constants. But for a normal graph or just a generic graph, it's going to be O of m plus n because there could be multiple edges, there could be cycles, and you have to take all of these into account. So yeah, in the example, it goes 1, 2, 3, 4, going down this kind of tree-like structure. Yeah, and then you start from the root or the source, whatever you're given in the problem. You could also just start from like 0, 0 or something. You could pick your own starting point, and then you explore all of that, the current nodes children from left to right, and put them into a queue. And then after you're finished looking at all of A's children, then you're going to move to B and add all of its children to the queue. And then you're going to move to C, to D, and then so on. So it's not terribly like complicated from like a diagram standpoint. It can get a little bit complicated when you're like implementing it on maybe a graph that isn't intuitively a graph. So if you're given like number of islands or something like that, that can make it a little bit more confusing. So, but does everyone get the overall or the overview of BFS? And for those who just joined, yeah, I'm just doing a quick overview, and then I'm going to show some implementation, and then we'll go into like 3 LeetCode questions. I'll give you guys like 10, 15 minutes to do each. But yeah, BFS. Go into the next one slide. All right, so here's an implementation. The left side is pseudocode. The right side is Java. I tend to do these in Java because that's what I'm like more comfortable in or most comfortable in. Maybe at some point I'll switch to Python because I'm getting a little bit more comfortable in that. So for the pseudocode, your input is S, which is a source node. And then you're also given a graph G, and then you set Q to be an equal Q, you enqueue S, which is the source node, and then you mark S as visited, and you can use a graph, a set, just an array to keep track of what nodes have been visited. It depends on the problem, and it depends what you're able to do. Then you're going to, or while the queue is not empty, you're going to dequeue an element from the queue. You're going to visit that element, so you're going to mark it visited, and you're going to add it to the queue. And you're going to do this for all of its neighbors or children in that graph. So neighbors if it's a normal graph, and children if it's like a BST or something like that, or some kind of tree. So that's the pseudocode. For the Java implementation, they use a Boolean array that's the size of the graph or how many nodes there are in the graph. And then you start at 0, you mark 0 to be true, or you mark n, which is the source node, to be true. Then you're going to add n to the queue, and then while the size isn't equal to 0, you can also use while q.empty is false. You're going to pull the queue, and so that takes the first the FIFO, the first element, out and removes it. Then you're going to go over all the children of that element. And so this is using an adjacency list, and you're going to add those elements to the queue, and you're going to mark them as visited. So yeah, that's about the implementation. Does that make sense to everyone? All right. So yeah, I'll just go to the LeetCode question, the first one. If I can. Okay. So this one is find if a path exists in a graph. I'm going to switch the share probably to what I'm currently doing. I'll just do it to my desktop. Okay, so you're given a bidirectional graph with n vertices each. Oh, whoops. Let me not show you all the code. So yeah, you're given a graph with n vertices labeled from 0 to n. The edges are represented as an array of edges where each edge of I has u of I to vi, and so that is an edge between u and v. Every vertex pair is connected by at most one edge, and no vertex has an edge to itself. So yeah, you're trying to find if there's a valid path from the source to the destination. So in the first example, you're given the source as 0 and you're given the destination as 2. So this one, you can pretty easily see that there's an edge between 0 and 2. So there's 2 paths for this. You could go 0, 1, 2. You could just go 0 to 2. So yeah, 2 paths. But for the input, you're given 0 to 1, 1 to 2, 2 back to 0. So you can also have that. It doesn't have to be like from the first node to the second node. It can be just any node to any node for the edge pair. So you see how it goes 0 to 1, 1 to 2. So that's in this direction. And then it goes 2 to 0. It can go in the opposite direction. But because it's a bidirectional graph, you go back and forth. Like it doesn't matter which direction it is. So that's one caveat to the question. So here's an example where there's not a path. So you're given source of 0 and you're given destination of 5. If you start like some kind of search algorithm or BFS from 0, you can never get to 5. Does that make sense to everyone? Yeah. Is everyone able to find this problem? I'll put it in the chat. Make sure. So I'll set a timer for like 10 minutes. You think that's good? And then I'll just go over the solution. While we're doing this, I'm going to stop to share for a second and fix the other questions so that I don't show the code. So how's everyone doing on the problem so far? It's good. You can also let me know if you have any questions or anything for it. I'm gonna give you guys like 3 more minutes and then I'll go over the solution. I'll just live code it. That works for you. Let me know if more time. You guys ready for me just to live code it? Yeah. Yeah. No.
Yes.
All right. All right. So first thing I'm gonna do is I have these edges that go from 0 to 1, 1 to 2, and 2 to 0. So I'm gonna figure out some way that I can use those um, in a more like directed way so that I don't have to check all the edges. Like let's say I'm going from 0 to 2 again. I don't want to have to check, all right, is this one included in is 0 going from 1 and then 1 to 0? Like I don't have to check the start and the end of the edge for if there's a connection between them. I also don't want to iterate through an array because that's going to be like O of M, and then it's going to be that like n times. That's going to be a really, or it's going to be O of mn. So I'm going to use a map to store the edges between, um, or I'm going to have a map that maps a node to all of its neighbors. So I'm going to have a map that goes integer and then a list of integers. So I'll just name this map, or I'll do edge map. So I'm just going to use a hash map from that. And then for a hash map, you can, it has O of 1 time for retrieving and updating. So that's why I'm going for a hash map. And then I'm going to iterate all over all the edges. And I'm basically going to add them to um, to each edge for both sides too. So here is one list. I'm gonna use the edge map to get or default for the first part of the edge. And if it's not there, I want a new array list. So this is just a helpful function that either gets or returns a empty list if it's not there, and then I'm gonna take that and I'm gonna add the second part of the edge, and then I'm going to update the edge map with the poke command. So I'm gonna take edge 0 and then the list. So I wouldn't have to do this if I was just getting a list that was already made, but because it can be empty, I'm going to have to use this put command. So yeah, I'm also going to do it for both sides. So I'm just going to take this and I'm going to approach it from the opposite side. So the index, so usually so what I did in the first part is I did index 0 maps to index 1. What I'm going to do is I'm going to switch them and I'm going to do index 1 maps to index 0 because it's a bidirectional graph. So that will make all my edges. And now I'm going to create a visited array. So I'm going to do the same thing that they did, or the same thing in the implementation with the Boolean array. So I'm going to make this visited, new Boolean, and I'm given n, which is the number of nodes. So I can just do it like that. And then by default, when you make a new array in a new Boolean array in Java, it's going to be set to false. So, which is what I want. So that's why I don't have to iterate through the visited array and set everything to false. So now I'm going to take the source and I'm going to put it as visited because it's what I'm starting with. Then I'm going to create a queue. Just going to name this queue. And it's going to be I'm going to make a linked list because that's just how Java does it. Oh yeah, integer. So now I have my queue. I'm going to add the start node to it, source node. And then I'm just going to breadth first search until the queue is empty. So while the queue isn't empty, so this not operator with queue.isEmpty. And then from here, I'm going to remove each node. So current node, queue.pull. So now I'm going to check if the current node equals the destination, then I'm done. I'm just going to return true. So yeah, eventually the breadth first search will get to the destination if you can. And so at that point, I just want to return true. Now I'm going to iterate over all the edges for the current node. So, and I'm going to use the edge map I made in this block right here to get all the neighbors. So I'm going to use current node. So now I'm going to check. So if it's not visited, if not visited because it's all false, then I'm going to add it to the queue. I think you can use offer. I think offer is the better like notation, whatever, but I just like to use add because can be applied to all like data structures in Java. So I'm going to add that edge to the queue, and then I'm going to mark it as visited. Edge equals true. So that'll, like this, if visited, will keep any cycles from happening. Because you don't want that. You don't want forever loop. So that should be good for my breadth first search. So if it can't find anything, then I'm just going to return false. Let's see if that works. Okay, so that worked for the test cases, and it should work for everything. Okay. So yeah, does that make sense to everyone? Go back to the PowerPoint. me for the solution. I have it right here. Any questions regarding this solution? No? All right. Well, I'll move on to the next one. This one is a little bit harder. And this is more what I wanted the workshop to be on because, in DSA, they already kind of go over like graph traversals. So I wanted to go over some questions that I'm going to drop this in the link, in the chat, but I wanted to go over some questions that you might not like intuitively think of breadth first search. So for this problem, you're given an M by N matrix with empty cells marked as just a dot and walls represented as a plus. So you're given the entrance and you want to compute the number of steps in the shortest path from the entrance to the nearest exit. So you can move one cell at a time, up, down, left, or right, but you can't step into a wall, and you can't step outside the maze. As soon as you get to a border of the matrix, then you've exited. Then you're done. You've exited the maze. So you basically want to compute like the shortest path from your current position to any of the exits. So I'll give you guys a couple minutes for this, and then I'll go into it. Probably the same amount of time, just so we can keep this within 10 minutes. Okay. Yeah, I'll send out the recording. And the slides are posted if you want to look at them, but I think the live coding, gives you a little insight into how to approach it.
Yeah, hey guys, it's James, workshop lead over here. I did post the slides in the slides channel on the ACM Discord, so if you're curious, go check it out over there. Thank you.
Yep. Is blind 75 good enough for most interviews? I mean, like if you can do every problem on blind 75, then yeah, like you'll be like great for interviews. But you want to focus on like learning the actual like algorithms and intuition behind each problem um because like yeah, even if you memorize every blind 75, like you're unlikely to get the exact same problem because they know that's where you study from. But some people do get the exact same problem. Like I've gotten a blind 75 problem before. Um, but I actually use or I used grokking the coding interview. I found that to be pretty helpful. I don't know about the like I don't think you have to pay for the course, but there's like a GitHub. Actually, I have it right here. Whoops. Yeah, I use this link. I'll send it right here. I like this one because it goes over. It has problems for each integral. I mean, each algorithm. So that's kind of what I'm basing these Leetcode workshops off. I'm not doing the same problems because some of them aren't that great. The one for breadth first search is not that great. So I'm not using those. But I feel like this approach might be a little bit better. Make sure you know all the algorithms pretty well, and how to do a Leetcode question with the algorithm, and then do the blind 75 as well. I don't know if that answers your question or not. Good. Yeah, no problem. All right, I'm just gonna go into the live coding now. If that's all right with everyone. All right. So first thing I'm gonna do is I'm gonna have the sizes because that just makes me not have to write this length every single time. Um, size. So I'm gonna save those. Next thing I'm gonna do is I'm going to I'm gonna get these. I'm actually gonna create my queue. So for this, I'm gonna do a integer array, and so this is gonna save the position as well as the number of steps to get to that position. So 0. So the row, then the column, and then the number of steps. So it's going to be 0 at first. So yeah, I'll create a queue. That should be fine for that. And then I'm going to change the starting position for in the maze to a plus. So that's how I'm gonna keep track of visited nodes. So I'm gonna say that you can visit a node if it's not a plus, and then for each node that I visit, I'm going to change it to a plus. So basically the intuition behind what I'm doing is I'm starting from the starting position and I'm running breadth first search on that starting position. So I'm basically turning this into a graph problem, even though there's no graph. So let's say in example one, you're given that starting position. I'm going to run BFS on that starting position, and it's going to give me the shortest path. BFS always gives you the shortest path between the source and any destinations. So there's like, that's just like a math, like there's like a proof for it and stuff. You don't actually have to know that, like know the proof, but BFS will always give you the shortest path. So now I'm going to run BFS on it while Q dot is empty. While it's not empty, I'm going to get the current node. I'm also I'm gonna have a couple helper functions for me. I'm gonna check for when, boolean, check, check exit. I'm gonna check if it's an exit. So I'll take in row, and then I'll take in the row size and the column size. So for this function, I'm just gonna have a little helper function to help so I don't have to write this every single time. So if the row equals 0, or it is, or let's do less than or equal to, and if it's greater than or equal to row size -1, I'm going to return true. I'm going to do the same thing for column. Call size. And then if neither, I'm just going to return false. So that just cuts down on the amount of code I have to write. So now I'm going to get the current position with the number of steps. So this is going to give me, yeah, the current position. So I'm going to have current row is current position of 0. All is the current position of 1. And then the number of steps is the current position 2. So yeah, now I have the current position, and I'm just going to check the 4 possible ways you can move: up, down, left, right. And I'm going to check if there's an open position. So let's do if current row greater than 0 and maze. So I'm going to go down first. Yeah. Row -1 doesn't equal plus. Then I'm going to check if I'm going to check the win condition. So check exit of current row -1, column, and row size and column size. Okay, so if that's true, then I'm going to return steps +1. Let's just put this on the next line. So that's the win condition. Now I'm going to mark it as visited. This maze of current row -1 and column equals plus. So that's basically just gonna mark it as visited or say that there's a wall there. It's the same thing because then you can't traverse it. And I'm going to add it to the queue. Current row -1, column, and steps +1 because I just took a step there. So that is basically what I'm going to do for each one. I'm just going to copy and paste it. Current row +1, and then I'm going to check current row less than row size -1. So yeah, that lets me, yeah. So I don't have an in out of bounds error. So I'm gonna change this to plus, this to plus, and this to plus. So now I'm gonna do the same thing for column. Current call greater than 0. Current call -1. Same thing. I change all these. So that should work for that. And then so this is going to the left. This is going to be going to the right. +1, +1, +1. Wait, am I using the wrong? Yeah, I am. Okay, I need to change all these to current call. Or I can just change this to call. That'll fix everything. That should work. Oh, but I changed all these. All right, let me just fix this really quick. That's an issue. Sorry about that. So this should run. It doesn't. There is an issue. -1. So you return -1 if there isn't a path to an exit. I just have an extra one. Means of current row doesn't equal plus. Oh, current row and current column. My bad. So, column and row here. This is right. This one. This is row. Row. Yeah, I got things a little bit messed up, but call. That's what happens when live coding. Row, row, column +1, row, column +1, row. Okay, so I think that should be fine. Oh, my bad. That is just a linked list, but I'm gonna save that. Yeah, so I'm gonna add it instead of do whatever I was doing there. Okay, so that should be good. There might still be an error, but if current call is less than -1, it would be, oh, whoops, that mixed up. Yeah, that should go the front. And that should go at the front too. Okay, I think everything's fixed. Okay, so yeah. Let me annotate this really quick. This is going down a row, so this is down. This is going up, up. So you're going up a row. This, you're going down a column. So you're going left. And this is right. There's a easier way to do this with saving the directions as an array and then iterating over that, but I find this to be the most like intuitive, like you can see it all, even though it's a little repetitive. So I messed something up somewhere. Let me check.
I think on the right case, you have current row twice. So that's supposed to be
Current row.
like on the very outer if statement.
Oh, oh yeah, that's a problem. Okay, there we go. Thanks, appreciate it. All right, so yeah, go to the next one. I'll just do that one really quick. Here's the solution. This is the LeetCode solution. It's a little different than I did it. They used a direction array. That's probably slightly easier or less code way to do it, and it looks a little nicer. The next one, jump game 3. So because we're running out of time, I'm just gonna just do this one really quick. But I'll go over the question really quickly. So you're given an array. And you can jump to, and you're given a start position in index. So at any position, you can either jump that position's value, or you can, you can jump that position's value to the right or to the left. So you can't jump out of the array, but you can jump backwards. And you're just trying to reach a index where the array value is 0, and then you're done. So for this again, I'm going to use a queue to keep track of your current position. List, same way as before. I'm going to add, I'm also going to have a visited array. Yeah, I need to do that so that you don't just jump in a cycle. Yeah, you don't want to jump like back and forth and back and forth. So once it's visited, then you can never visit it again. And you're given the length. Yeah. So you're gonna add the start position. That's the first value. You're gonna change that position to true because you visited it. Then we're gonna run breadth first search. While queue is not empty, you're going to get the current position in current position. We'll do index. Index equals q dot pull. So you're going to pull the first position off the queue, and you're going to basically search it. You're going to go to the right or to the left by that value. So I'll do a next variable. Next index equals the current index plus the value of the current index. So if the next index, it tells you that you have non-negative integers. So you don't have to check for it being greater than 0. You just have to check that it doesn't jump out of the array. So it has to be less than array minus 1. Yeah. And it hasn't been visited before. Yeah, and visited. So if it hasn't been visited before, you're going to add it to the queue. Actually, this is fine. You're going to add it to the queue, and you're going to mark it as visited. Visited of next index equals true. So it's visited. So for the current index, you're also going to check the win condition. So you're going to check that it's equal to 0. If it is, then you're done. Return true. And then after BFS, you're going to return false because you didn't find an index that's equal to 0. So yeah, that is if you're going forward. So it's going to be pretty much the same thing for going backwards, except you're going to minus this. The next is going to stay the same. You're going to change this condition to greater than 0, greater than or equal to 0. So that means so you can't jump out of the array. And that I think is fine. Okay. So let me just make sure. Okay, yeah. So when you're given something like this, specifically like a jump game or something like that, you can start to think of it as like a graph, where each one is kind of connected. Each index is connected by an edge, and that edge is however far your value is, in this case at least. So even if you're given arrays or 2D arrays, sometimes you can visualize them as graphs, and it makes problems a lot easier to solve. Does that make sense? Like my solution for everyone? I went through it pretty quick, so let me know what you think, or if you have any questions about this. I think this one's a lot easier than the maze game. But if you're just approaching it, it might seem more complicated. Yeah, does anyone have any questions? I think this is everything I kind of wanted to cover. I have the solution on the slides too. I should probably put comments, but I don't really like to use comments. I should start liking to use comments, but whatever. Yeah. All right. Yeah, that's about it. Does anyone have any final questions? Let's see. Thanks. All right. Thanks. I'm also recording this so I can post it. All right, guys. Yeah, thanks for coming.